Good morning, everyone. Thanks, Neil. Yeah, I'm Ron Bose. I'm with XPS. That's Glencore's technology consulting business. I've been implementing technology in mines for nearly 15 years now, and in all cases, it's in reaction to an identified need. So, in other words, the need happens, and then, okay, we need some technology to manage that. The initiative we're talking about today has been conceived differently. So today while many operations are still grappling with implementing autonomous or even teleremote mobile equipment, Christian and Kenneth's team have been developing a system which will allow manned vehicles to safely share the same ground as autonomous equipment. So the belief in this concept is very strong, and the technology is going to be debottlenecking underground operations before we've even recognized the bottlenecks. I'm really looking forward to the presentation today.
Thank you. Christian, Kirill. Christian? Oh, I don't think we can hear you, Christian. You're showing that you are talking.
Okay, I thought it was that Christian you were asking for. Sorry.
No, it was for Christian Kirill. Sorry, Christian Grant. We have two Christians involved with this project, so it gets a little confusing. I think Christian Kirill is having a hard time connecting with his microphone, judging by it. So we'll just move along, and we'll come back to him. I apologize to everyone, including Christian Kirill. So Christian Grant, I'll pass it over to you.
Yes, I will get cracking. So starting with, let's see if you can you see my presentation? No.
Yes.
Excellent. So let me get started. So first going short into the background and then diving into the project that we have ongoing in GMG. So basically, as you know, automation have definitely benefits, and we can see what we are mostly targeting with automation today is safety, basically moving our colleagues out of harm's way to safer areas. Of course, looking forward, would like to make mining more pleasant working environment so that we actually have more miners in the future. But of course, then productivity. And we see great potentials in productivity. The picture you see to the left is measurements, and it's fairly old picture. I think it's 15 years old. Down in the Boliden area at the mine called Renström. You can see the dark blue. It's actually the shifts and the activities that they have on the face. That dark blue adds up to about 25% utilization of the mine. And then at the same time, simulations were made. That's the dark green that you see there. And basically suggesting that if we had automated and operated machines in the operations without any other investments, without changing the process, we could reach about 50% utilization. That would be 100% higher productivity. That was actually what kicked off the automation program at Boliden. For the last 15 years, a lot of work, and you have seen that in the mining community, has been going into basically robotizing the machines, making the machines automated. And this is a normal tunnel process. And we have basically developed so that we have machines for each operation that are, if not completely automated, semi-automated. The last one we have left is really charging, and we have an ongoing project here, and you can see that's a bit unusual mining machine. It's actually a normal manufacturing robot fitted on the back of a truck that actually can do the charging, which means that we cover the complete process. However, when we are rolling these machines out in production, we're not seeing the productivity that we expected. Actually, in many cases, the productivity is lower than that we have utilizing manual machines. So when we looked at the problem, it becomes quite apparent that the problem has to do with the safety of the machines themselves, or rather the way we implemented it. We basically locked them up in robot cells. It's a super straightforward way of proving that the machine is safe, that you are safe from from potential harm of the machine. Now, the problem then is then that it's not only one operation, not one process ongoing in the mines, as you know. So even if we prioritize productivity, if we don't have maintenance, if we don't have a further development of the mine, also production stops. So in practice, in many mines, we basically have a lot of standstills because people need to enter the robo cells, and you basically need to stop the automated machines. It's not a unique problem, so we can see this in the manufacturing industry. When they in smart industry and industry 4.0, it was a lot of talk about lights out. The last worker turns the lights out in the factory, and the production just keeps going by the robots. It hasn't shown to be a success. So in industry 5.0, it's a lot of talk about cobots, collaborative robotics, basically where we are utilizing the robots for repetitive tasks, and then have people in that are innovative and can solve problems, cooperating with robots. And we expect that we need something similar in the mine. Now, in mining, when we go into academia, the field is basically called field robotics. It refers to mobile machines, or rather mobile robots, working in environments like space, construction, and mines. So what we need to head into would be something like field cobots. So this is what we are exploring in this project. The opportunity looks good. So this is simulations, but this is also from a Boliden mine. It's from a new mine called Rävliden, where we basically have a decline down to the new mine that is about 5 kilometers long. And the idea is to deploy an automated hauling system, but we also then need to have all the machines, all people going down and up, going into the same decline. With a static geofencing, basically what we have now, a robot cell, and if we enter into the robot cell, the automated machines have to stop. Then you can see that the utilization would be good in the system if we don't disturb the system. Basically, if we don't go into the robot cell. And of course, the more frequent we go into the robot cell, the less utilization we get from the automated machines, because they are basically standing still. This is exactly the problem that we see in many of the automated applications that we have today. We then have done simulations with dynamic geofencing, basically where we only stop the automated machines if we get close, dangerous close to the machine, which shows then a high potential in increasing the utilization, as you can see, the blue line on top there. So what's the problem? The problem is really to assure the safety of the people working close to the automated machines. So the tools that we have today is basically functional safety, and we also have something called system safety. So I would say the definitions really of what functional safety and system safety is probably as many as there are safety engineers. However, GMG has really good white papers on this. So you can do look into the white paper on functional safety, and there is also one on system safety. So this is my way of viewing functional safety. Functional safety is super good when it comes to problems with electronics, basically hardware. So if you have a control unit, like when I started my career, I was working with the ESP systems in the cars, the anti-skid systems. And then we basically had an IMU inside of the system itself. Then functional safety is definitely good enough. However, we make assumptions about the environment around us, called operational design domain or something, and those are assumptions, making it hard to prove what is outside of the system. It's similar, not exactly with system safety. System safety is most often, at least where I've seen it heavily used, is in aerospace industry, where you basically, instead of saying that, as in functional safety, that my electronics and software needs to be good enough for the environment, you basically say that you have an accident model and all the problems then that you can cause is a control problem that you need to consider. However, also here we make assumptions about the environment and we argue about the environment. So with learning, me and most of the team that are part of our project come from the automotive industry, and we have been part of this automation hype in the automation industry, where we believed strongly in our systems, but we had a hard time actually telling the management that the systems were safe enough, or rather they asked us, are you sure? Can you prove that they are safe? And it's really, really hard to prove that something is safe when you have a sensor and you're looking into something that you don't really know what it is. So for this system, we basically came up with some principles that we need to be able to say that we are proving safety. So the principles are that we need measurable safety over subjective judgment. We need a defined limited context over vague context. We need proven arguments over claims. And also then we push basically the moral concept out of the engineering part of defining the risks, which means that we go into something that is proven instead. So in this project, as Neil, you said, we intend to publish 4 white papers that I really would like your help with. So we have first one that we call the theoretical foundation. That is more an academic paper, basically giving the academic background to what is proven and what is proven safety. We have one on technical implementation, basically telling you that yes, it's possible to build such a theoretical system. And then the intention is then to publish a white paper on industry application, basically saying that when you utilize a new technology, you can't just keep working as before. Then the technology will most probably fail. So you actually need to adapt the way of working, change management. And the last one is basically then targeting how to evolve the industry, creating an ecosystem where we can run mixed traffic and utilize this kind of technology. So back to the problem. The problem that we have when we want to prove that something is safe with the tools that we have today is that we definitely can prove the computational part. And that functional safety is good at. We can prove the controllability, but we definitely have, when we want to go to proven safety, a problem with measurement and how we measure, since these systems are basically control loops, right? So going in where we have a sensor feed that tells us about the environment outside of the vehicle. I will go into why that is hard to prove. And then we have the feedback going back. So we need, if we want to prove safety, we need basically, for a formal proof, we need control of the complete concept. So the approach to proofs, yeah, at least to my knowledge, we basically have two ways that we can go. We can use statistics. Statistics is basically that we try the system so much so that we know that it's safe, and then we statistically can calculate how many hours we need to run the system to know that it's safe. And then we have formal, which basically means that we use math, we prove it formally. And we have something that is slightly in between standards, where we basically have a standard that we have agreed upon, I would say society, but mainly in the industry, that if you utilize the principles, then it's safe. Here you have the numbers that most of the standards utilize. If we continue, so the statistics, I just nicked this from a paper. It was published, I think, in 2016 by these gentlemen. And they are talking about how much testing you need to do if you want to prove that a car is safe, an automated car is safe on the road. And if you look at the numbers, they are fairly high. This is basically just statistics, and probably the first class of statistics that you had, which means that if you just meet the requirements with your system, unfortunately, the amount of testing you need to do to prove that it's safe goes towards infinitive. If you have a system that is better, so that you can see on the y-axis here, you can see if you have a system performing better than the requirements, you can start proving it. And then depending, of course, on the parameters you put in, you basically get a number of how many hours can you expect to prove the system until you shown that it's safe. And if you then take the basically safety that you will experience if you're driving on the roads in the US, you end up with 11 billion miles. That's about, it depends on how you calculate, but it's about 2.5 million hours. Sorry, that's the requirement, 2.5 million hours, which means that you actually need to test the system for about 30,000 years. And if you then see the requirement ends up here at it would be when you go to our standards on the sea level 1, 2.5 million hours would the requirement be. That's the safety level that you have in traffic in the US, performance level B. And you can see we are in our requirements for the industry about 10 or 100 times that, which means that you would need to test your system for 300,000 or 3 million years, which is possible if you have a big fleet, but it's really, really hard if you have a small fleet. I had an example where the team is in Sweden, so we looked at the Viking ships. So if we had utilized all the Viking ships that were built 1,000 years ago, they would actually still be sailing to try to prove the safety if we had installed such a system of the Viking ships. So it's a lot of testing that you need to do. Now, instead, if you go the formal way, you need to go basically through math. Math is based on axioms. So the theoretical foundation, it basically then gives you goes from the axiom, and it goes to the from the very fundamental axioms. So if you do believe that we have points and that you can draw a line between points, then Kenneth has basically built a proof for the number system, the geometry, the math, the physics that we use, the logic, and then we use some computer science in this. So the idea of why going back when people have done this before, it's basically because some people had really nice proofs like Newton, but as we know, Einstein discovered that Newton's axiom was wrong, right? So this paper builds it up. It basically builds up how you prove a formal system. So if you really want to dig into this, I would suggest that you set up a session with me and Kenneth, and we will dive into the theory behind. It's two things that I really want to point out in this, and that we are utilizing, and where we had challenging in finding ways of proving. And the first one, it refers to Gödel here, and it refers to Gödel's incompleteness theorem that basically claims that if you want to axiomatically prove something, then it has to be a recursive set. You basically have to be able to reach all the states, but it also has to be a limited set. And then we also needed to find a way when we go to physics, when you do measurements, you basically create distributions, which is hard to formally handle. We found a way. So first to Gödel. If we would have a machine or a vehicle with a sensor on looking into an environment that is unknown, we basically don't have a limited set. We can't build a formal proof. So in this case, we then instead used a strategy that has been researched. I know that Nokia and Ericsson did a lot of research into floating vehicle concepts in the 90s. It's basically just that each actor in the system communicate their position centrally, and you know everyone. So we turn the problem around. Instead of having one vehicle machine looking to something that is unknown, trying to prove that it can see someone that it doesn't know if they are there or not. Instead, we basically turn the problem around, saying that we can see everyone, all the actors in the system all the time. That means that we have a limited set, and we can then build the formal proofs from it. When it requires communication with integrity, that's not an issue. There are a bunch of ways to set up the communication. Also make sure that you have everyone in the system creating heartbeats. The difficulty for us was the location, because we need a formally proving location, which means that we basically need to make a formally proving measurements. The way that we decided to do this is basically to use time of flight. That goes back to what we can and what we do know in physics is that nothing can move faster than the speed of light. So we have, in this case, we have anchors. That's infrastructure, radius in the infrastructure, and we have actors that also have radius. And then we measure the time of flight between the anchor and the actor, which means that we know the time it took, and by knowing then the speed of light, we can calculate the distance. Now,
Hello?
Yes, hello. Okay, I continue. With time of flight, we can do a three-lateration. So the challenge for us was that triangulation is not really possible. We couldn't find a way of proving the angle, but we can prove the time of flight. And the time of flight, we can just prove that we haven't measured too short. It can be a too long measurement. It can be a reflection. It goes through something that isn't vacuum. Radio waves can even bend in our mining environments, which means that you will most probably end up with a measurement that is too long. So but we can prove that if we have a system that have integrity, we can with that integrity prove that the measurement that the actor that we measure to from the infrastructure is within this circle, or rather in 3D, the volume, the sphere. This means that we have a hard time improving a safe distance if we do vehicle-to-vehicle measurements, because we can measure too long, which means that we can believe that it's safe, although it's not safe. If we use infrastructure, which we anyhow have to do to make a floating vehicle concept, and we can measure from the infrastructure. If we measure too long, we still know that the actor is in this space. And if we have several anchors, you can see that we get a set, we get a more limited space, and we can say that the actor is in, or rather the radio is in that space. Or if you do it the safety way, you basically say, yes, we know that it's not outside of this space. Make sense? Right, Neil? Yes, thank you.
Yes, sir.
Which means that we actually have an area where we know. So this is a localization. It's not the exact position, but it's a localization which we can prove. And those are basically the fundamentals in the first white paper that we intend to publish. It's basically axioms and the way how you can prove something. And we found a way that we can create a mixed traffic system. The second white paper that we are working on, and this is an engineering paper, it requires a lot of more effort, and it's Boliden, LKAB, and BHP that are actually sponsoring the project, because to know that we can build the system, design it, we need to try it out, right? So this one, and that's why Neil mentioned Kite Shield. The project is called Kite Shield. But we are utilizing this research and advanced engineering project to then write the white paper on the technical implementation. So what we have done so far is basically, yes, we utilize the localization to create proven situations, and then use the proven situations to create the threat assessment. And if the risk becomes too high, we basically stop the automated machine. This, I hope that you can see. Can you see a film clip? So here you have a digital model. This is Rävliden that you saw before, the Boliden mine, where we have a test system set up, where we did the feasibility study. Here you see that the safety bubbles are not nice because radio isn't nice. So you can see here 3 anchors. We do this with ultra wideband, creating then a volume. Here we add on the footprint of the machine, but we don't know orientation, so you can see it goes also in the set direction. And we add on the dynamics, basically the stopping distance of the machine, which means that we then can stop it before it interacts with a manual machine. To be able to pass what we really wanted to do, we have a safe state where we can park and guarantee that the automated machine is standing still and we can pass it. and then you can see the safety bubble comes on. Here you can see that you see on the screen, you see a digital twin stand in the pocket, here, meeting pocket, and you can see that there is a pickup on its way from below, and we have an automated machine on its way from above, and they are driving too close, which means that it triggers the safety system. You can see it goes off here. The manual machine warns the driver, and the automated stops. We designed the system. It's basically just the safety system, so it's not an automation system. We are only doing the safety part. The only thing it can do is to stop the automated machine. So it's completely separated from the production system, basically the automation system that is creating the productivity, traffic control, fleet control, operation control, vehicle control, that we are not dealing with. We are just dealing with the safety system. If the machines get too close, we stop the automated one. That's how we implemented it. Just showing the implementation of these anchors or satellites. We designed them. We needed to be sure that we could make a ship design, basically, because it's a lot of anchors. We have one about every 15 meters in the mine. So we put them on a cable. This is a normal long cable. You have the anchor on, and you basically just wheel it out, and you put it on. It's not big, so here you can see you have it's about the size. The electronics is about the same size as a credit card, as you can see here, and light. Here you can see this is we have one system also implement test system in the Kallio test mine in Finland. And here you can see this is actually you can see the installation on board of the vehicles. You have driver interaction. You can see a part that is on top of the car there, and we also then have laser gates that we use as sluices to enter the system. That's basically the technical implementation. Now, Boliden and LKAB and HP, they actually decided to continue working on it. We proved the concept that it's feasible to design, and they actually decided to continue working towards a solution, and most probably a product. It's not intended to be a profitable project, but they are asking for other companies to join here. Of course, it's engineering work, and it's high integrity safety work, so it requires some funding to drive this, continue driving this. And the third white paper that we haven't started yet, as I mentioned, it's on industry application of the system, where the intention, and we really would like people's help here, is to look into how would this kind of technology be adapted into the processes that we have in our industry. Basically saying that if you're taking a new technology and just run things as you usually do, it will probably fail. We need to adapt the way we're working to the new technologies. This is the intention with this paper. And the last one is basically then looking into how we can build this into the industry. It has been a challenge. So we run research projects where we basically been a bunch of companies pulling technologies together. We are now establishing a consortia, and we just called the initiatives that are going to build it the Forge, since the project is called Kite Shield. If you buy me a beer, I will tell you the story behind the name. But we really would like to look into how can we create an ecosystem where they basically the US mining companies handle the governance of it, and it becomes a self-sustainable ecosystem. So yeah, just to sum up, our ambition is to establish mixed traffic and do it by proven safety. The project ongoing with GMG, we would love you to participate in the implementation project and also in the projects where we are looking into how to apply this in industry. So to join us